All right, folks. Thanks for joining us. And today I would like to introduce to you Brandon and Jenna, and they'll be discussing about productionizing machine learning in health and wellness market space. Jenna is a machine learning engineer at Mindbody building products for customers and consumers in the health and wellness space. Previously, Genna was a data science consultant at Oliver Wyman and specializes in providing machine learning solutions to our clients. Genna was an organizer for WiML 2017 as the student liaison chair. Brandon is a machine learning engineer at Mindbody with a background in software engineering and API development. He brings his experience to the MLOps space to lead the ML team's effort in data engineering, as well as deployment, monitoring, and integration of ML services at Mindbody. Without further ado, I will leave the floor to Brandon and Jenna. Thank you.
Excellent. So I'll get us started. So hi, everyone. Today, Brandon and I are really excited to speak to you about our experiences building machine learning services for our health and wellness marketplace. So I'm sure this audience knows how tedious and time-consuming it can be to bring trained machine learning models into production. We've definitely experienced this at Mindbody. So today, we're going to speak about how we address that by leveraging open source tools to design workflows around reusability and scalability that drastically reduce the time it takes to bring our services into production. So I'm going to start by introducing you to Mindbody and the types of machine learning products that our team builds. I'll then dive into the details about the recommendation services we've built for our health and wellness marketplace. And then I'll hand it off to Brandon to describe how we productionize these services. Specifically, he'll speak to the challenges we faced and how we went about addressing them. So let me briefly tell you about Mindbody. We are the leading software provider for the health and wellness industry. Our mission is to connect the world to wellness, and we do that through two types of product offerings, Mindbody Business and the Mindbody app. So Mindbody Business provides software for studio owners that offers scheduling management, marketing, and anything the owner would need to run and expand their business. The Mindbody app is probably what you're familiar with if you've used our services before. It's the one-stop shop where you'll find and book all of your fitness, wellness, and beauty needs in our global marketplace. So the AIML team was formed in 2019 for Mindbody, and we are charged with the mission to build machine learning-powered services to complement our business and marketplace software. So on this slide are some examples of the types of machine learning features that we are developing for our B2B offerings that encompass a full-service machine learning-powered business advisor suite. So within this sector, there's a wealth and variety of opportunities to provide machine learning services to help our studio owners automate running their businesses. For our consumer-facing app, the machine learning opportunities that complement an online marketplace include things such as recommendation engines, personalized search, personalized campaigns, and trust signals or data tagging. So today, we're going to focus on a couple recommendation engines that we've built for the marketplace. So with that, let's jump into the problem we're addressing with these recommender systems. So this is our consumer marketplace. On the left, you have an enormous number of consumers, each with many dimensions of preference. This can include things such as fitness modality, location, willingness to spend, or instructor preferences. Then on the right, you have an enormous number of providers, each with their own unique value proposition. So today, our marketplace is a booking utility. This means a consumer enters knowing what they want, books it, and then leaves. So we want to shift our booking utility into a marketplace where our consumers go to find their next favorite fitness class through rich, meaningful discovery. So we're doing this by building recommender engines that enable this discovery by pushing relevant recommendations and offers to our consumers. So to date, we have launched two different recommendation engines. One for dynamic price offerings that offer last-minute classes at a discounted rate, and one for our virtual fitness class marketplace. So the dynamic pricing recommender is designed to increase purchases by surfacing relevant offers to the marketplace consumers. The approach consists of an ensemble of collaborative filters and a content-based recommender to personalize the recommendations. The end-to-end development cycle for this service was about 9 months. The virtual class recommender is our second system that we've built, and it was designed to increase the diversity of inventory that is surfaced to the marketplace customers and is actually 3 recommenders in one. It ensembles a couple of different collaborative filters with consumer data in different ways to provide diverse sets of fitness class options. So we were able to apply some of the learnings from the dynamic pricing recommender and shorten the development lifecycle for this system to about 5 months. So now the next recommender we want to build is a general recommender to provide personalized recommendations to consumers for all of the health, beauty, and wellness offerings in the marketplace. Our goal is to reuse the work that we've done for the previous 2 recommenders to dramatically reduce the development lifecycle and rapidly put this new recommender into service. So now that I've introduced you to the problem setting and the machine learning approaches that we took to solve the problem, I'm now going to hand it over to Brandon to talk about how we productionize these services by reworking our MLOps architecture to produce a framework that dramatically reduces the time it takes to launch a new recommendation engine.
Great, thanks, Jenna. So now you've got a feel for the problem that we're solving. Now on the engineering side, what goes into making this all happen? And I want to take a step back and ask a question. What goes into a machine learning project? Most of the time when we think of machine learning, our first thought is that box, that highlighted box right there in the center, your ML code and your models. Now this diagram, this is a very popular diagram. Maybe many of you have seen it. This was put together by the Google Cloud team. And I think it does a really great job at highlighting just how complicated it is to deliver machine learning, right? I mean, we have a whole conference on it. 2 things that I really think this is helpful, that it really helped me understand is first, the model selection and ML development effort is only one task in a large list of engineering work for delivering machine learning, right? There is a lot to consider and think about when you sit down and you plan your projects. Second, the relative effort of model development is actually relatively very small compared to things like infrastructure, data and feature engineering, tooling, deployment, monitoring. And that's why it's often said that 9 out of 10 models never actually make it to production. And for us at Mindbody, this diagram is very real. We're often done with training and tuning our models months before we're actually able to deliver them because of all the extra work that goes into it. And one more way that I like to think about this is by dividing a project into 4 categories. To make our project successful, we need to invest in all 4 aspects of our products. And I like to think of them as levers or gears where, if you invest if you invest time in one of these things, it's going to have a multiplying effect on the success of your project. But also on the flip side, if you neglect one of these things, it might actually limit your effectiveness, no matter how great some of the other components are. So it's a bit of a balancing act. For example, think about an engineering team. They focus heavily on the ML data science portion, and they build some really, really great models which have really great predictions. But they didn't spend very much time considering the UI and UX. You're going to have a great model, but it's not going to be very usable or very effective. In our case, we realized that the areas we needed to apply some focus to were these bottom 2 elements, our data and our infrastructure. For data, right, we all know that clean, quality, representative data, this can be a deciding factor between a good and a bad model. And on the infrastructure side, similarly, if you don't have the infrastructure to support the amount of training, the deployment and testing that to really support your development and your shipping goals, you are going to have a serious delivery bottleneck. So our MLOps team, what we did was we took a step back and we started to drill in, okay, how can we improve our data and our infrastructure so that our platform can have a multiplying, this can have a multiplying effect on the success of our current projects, but also all of our future projects. So here's a rough layout of what our recommender systems look like. It was really just a natural progression. First on the left, we were given the task, build a dynamic pricing recommender. So we went to our data warehouse, we copied over a data set, we used it as our training data, we engineered some features, we trained a model, we built an API. Our APIs are built with Python Flask, deployed in Docker images on Kubernetes. And so we deployed that. We needed, our consumer features to be in a fast production database at time of serving. So we built a pipeline to compute those features, upload them to production, and it worked. This recommender is out in production. It's serving traffic. But then it was time to build our second recommender, our virtual class recommender. And so we followed a similar process, right? Data acquisition, feature engineering, model training, API built, deployed, data upload, and done. And that one's out too. And both of these, they're deployed, they're serving traffic. But now following this pattern, imagine what would happen if you want to build a recommender number 3, 4, 10, right? Or even just a different machine learning project that might use similar features or patterns. This method of development is going to come with some obvious pain points. First, duplicate data sets and duplicate feature engineering efforts. Really what we did with each project is we started from the ground up every time. And the drawback is that for each consumer, we needed a lot of the same features, right? For these recommenders, we looked at things like past visit history, past sale history, aggregates, right? Aggregate sales by category, time of day of week preferences. And each time we start a new project, it almost was like we were reinventing the wheel or going back to the raw data, maybe even just copy and pasting massive SQL queries from one project to the other. The next pain point, we had redundant models with no sharing mechanism. In order to just deploy these quickly, we were using the AWS infrastructure with Pulumi infrastructure as code. And so each of our APIs would pull the models from separate S3 buckets that were dedicated to those services. And so, you can see here, we actually have model A in both of these. So we were just copying files over, putting them in from one S3 bucket to another. And really, we just did it because we didn't want to rock the boat from the previous pipeline, right? We just said, okay, let's just build a new pipeline for this one. And then the third one, recurring jobs are non-standardized. They're difficult to manage. There's low visibility. And it's not explicitly drawn here, but most of these arrows require some sort of automation and orchestration, or even just a manual job, right? Model training, the data upload, that's a job. Evaluating a model, data processing, data ingestion. And for all these things, what we did was we kind of just followed the path of least resistance. For model training, we need a large compute instance, so we SSH into an EC2 instance, run our model training. For model evaluation, we want that running regularly, so we said, well, we're using Kubernetes, why don't we deploy cron jobs onto those clusters and run those? Or data upload, we were thinking about maybe cron jobs, sometimes we even used our CI/CD build agents, and this just led to a disjointed platform. It was impossible to manage and almost impossible to monitor. Again, the biggest problem here is scalability. I think it's really easy to imagine how this is going to break down when you want to build not only just other recommenders, but a really great ecosystem of high quality machine learning at your company. And another thing, on paper, this seems obvious. But often when you're deep in a project, you're dealing with deadlines and requirements. Sometimes the fastest way forward, it seems like it's to just kind of get that tunnel vision, build out your single pipeline. Don't think about other projects and distractions and just get it done. But actually, this is the wrong way to go about it, right? And what we did was we took the blinders off. And we started to address these pain points. We realized that a lot of these pain points could actually be easily solved with not a ton of effort. And there's a lot of great open source tools to help us do this. So let's dive in. So the first pain point, there was duplicate data sets and feature engineering efforts, like I said. The solution to this is we developed a feature store. Now, feature store isn't just a database, it's actually an ecosystem of databases, queries, data transformation code, and it provides our ML pipelines and our ML services with unified access to the features that they need for machine learning. On the data store side, we think about it in two ways. We've got the offline feature store, which has all of our data for model training. It's versioned, all of our model training jobs and evaluation jobs can pull from there. And our online feature store, which is meant to be lightning fast, used for model serving at time of prediction. And the key result here was that we had standardized access to the features, the data pre-processing directly from our API code and our training code, making it very easy to reuse our features. And some tools we used here is we used DBT, which is an open source tool for documenting and storing and maintaining your data transformations, your SQL transformations. And then also Great Expectations was something that we're starting to leverage for testing our data and enforcing the quality of our data. So what does it look like now is instead of our swim lane architecture, it's more of a fan out architecture from our feature store. And we have our offline and our online feature store. And this is the one place where we can manage data, access data, generate features, sync data between your offline and online environments. And I like to think about this as almost like feature as a service, right? All of our models are trained off of the same place, and all of our APIs get features served from the same place. And you know, any new features that anyone on the team works on, they're immediately made available to the rest of the team. And so it's a bit of a paradigm shift, right? Instead of a feature being a recommender feature, right? Or a smart subject line feature, or a lead management feature, whatever project you're working on, it's just a feature, right? It can be leveraged by any team, any project for whatever use case, if it works for that use case. All right, next pain point is we had redundant models across systems with no sharing mechanism. And so to solve this, we're leveraging MLflow's model registry. And the model registry, it's a centralized model store to collaboratively manage the full model lifecycle of a model. It provides model lineage, model versioning, and stage transitions. So you can have a model that's in staging, and when it's ready to go to production, you can tag it as, you know, go to production. Then when the services go live, they can pull down the latest production model. And so the key result here, yeah, we can share models across services, maintaining the traceability and the performance of these models. So now we've added in the model registry. And similar to the feature store, we have a single place where we can get the benefits of our trained models accessible from any machine learning service that needs it. One thing I want to highlight is we originally had 2 model training pipelines for this model A. Now we just have 1. You know, also there's no complicated deployment steps. We're not copying models between S3 buckets. And similar to feature store, our models are no longer, you know, recommender 1 models or recommender 2 models. They're just models, right? And anything in our ecosystem that needs these models, any new service can pull these models down. So we can share models across systems very, very easily. And lastly, pain point 3, are recurring jobs. They're very, very hard to manage, very hard to monitor. And so what we did here was we're leveraging Airflow. We said we need a centralized orchestration tool to programmatically author and schedule and monitor all of our workflows. So Apache Airflow is working great for us. It allows you to manage all your jobs as DAGs, you know, which is a visual there's a visual representation to see the stages of the jobs and how they can depend on one another. One example down here was we had a model training job. First, it executes a query, gets fresh data, it retrains models, it computes metrics. And one thing that I thought was pretty neat is for our model training, you know, you can still leverage high compute resources because Airflow really is just orchestrating, right? So what it's doing here is it's actually orchestrating SageMaker to pull down a Docker image of one of our model training jobs, and then it runs it on SageMaker, and that's working great. And so here we have our updated orchestration tool. It manages pretty much everything. Our model training on the right, it manages our feature store data transformations. It manages our data upload from offline to online. Some other things it manages is like our evaluation jobs, data ingestion from other places. And additionally, for monitoring our jobs, now this is great. We have one place to go where we can see what jobs are running, what jobs are passing, failing. We can look at logs for the jobs. And so, yeah, this orchestration piece it was key for us. And so here's our updated architecture now. The biggest highlight for me is that we made a mindset shift. And it's a mindset shift from project focus to platform focused. So now when we're given a new project or we're trying to solve a new problem, rather than thinking, okay, how are we going to solve this problem? We think, how are we going to solve this problem, and how is it going to fit into the larger platform, or maybe even add to the larger platform to build out an even better machine learning platform that's going to have a multiplying effect on the success of our company and our team as a whole. And so with that, I'll pass it back to Genna for some of our key takeaways.
Excellent. So now the question is, what did we get out of investing in this work to make this mindset shift? So there are 3 key takeaways. First, we have a better platform for maintaining our services. Instead of multiple services doing the same thing, but in slightly different ways, we have a single framework to monitor and maintain. So second, the feature store has provided us with a centralized and consistent data framework. Before, our data processing pipelines were branching off from the data warehouse, and it was up to each individual engineer to determine how to define something such as a consumer visit. So this led to a lot of inconsistencies in our data processing and a lot of repetitive work. So now the feature store centralizes all the logic and data transformations so that our engineers can use each other's work. And then lastly, designing our framework using reusable, scalable components allows us to reuse code across all of our services. This means no more reinventing the wheel and allows our machine learning engineers to focus on machine learning instead of software engineering. So then the key result of this platform rationalization and consolidation is that we were able to dramatically reduce the development lifecycle of launching a new recommender service by over 85%. So now we've gone from a 9-month release cycle down to a 1-month release cycle. So not only does this benefit our machine learning team, but from a company perspective, it lowers the barrier for other product teams to work with us to rapidly incorporate machine learning services across all of the Mindbody products. Excellent. So thank you very much.
Hi, folks. Yeah, thanks so much for the interesting presentation. So we have a few questions here, and I'll probably just read it out to you guys so you guys can answer that. One question from Shuai Peng is, what tool are you using for the feature store?
Yeah, so it's kind of a combination of tools. On the offline side, we are leveraging the same technology our data warehouse is using. So it's a Snowflake data warehouse. So we've got a separate account that we use just for that and a separate database for feature store. And then to manage all the different transformations, right now, most of our transformations are SQL transformations. So we're using dbt, and that's an open source tool. Then for online feature store, we're finding that DynamoDB is really fast. So we're just doing some data uploads from the offline to that online Dynamo database.
Got it. Awesome. Thank you. One more question from Manisha Singh. Could you explain the function of the orchestrator?
Sure. So it really is just Apache Airflow, which just allows you to manage all of your different workflows. And so we have a repo that you can save all of these DAGs that you just write as code. And then they have all the different steps there. So, we have a DAG for our model training. We have a DAG for a data processing job, or a DAG for an evaluation job. And then when we go to that Airflow, it has a front end too. So you go up to the Airflow front end, and you can view all the different jobs, and there's red, green check marks for, what's running and what's not running.
Awesome.
But one thing to note on that, so the orchestrator, it's not actually running any of the jobs itself, right? Or its compute resources are not running them, right? It is actually just telling other resources, hey, go run this, go do this.
One more question from Rajiv Abraham. When you tag a model with the production tag in MLflow, does MLflow have integrations on initiating the deployment to various cloud-based infrastructure? Is CI/CD done by MLflow?
So we actually are hosting MLflow our own, like in-house. So we're actually just taking the open source MLflow, and so we've actually got CI/CD for MLflow as its own service to keep MLflow up and running.
Okay.
So it's actually within our cloud environment.
Got it. I do have two quick questions for you. So I know you did talk about like the turnaround going from 9 months to 1 month, but then now my question is that cold start is always a problem with recommender systems. So if you were to start from having zero data, how long will it take you eventually to come to the stage you're in? I mean, with the cold start problem being an issue.
So all of our recommenders institute a cold start solution. And it's really up to the machine learning engineers to kind of develop and validate what that is. And so specifically in our marketplace, we have a notion of the average consumer. And so we use the average consumer as our cold start solution.
Got it. That's awesome. That's great. Final question. Well, I guess there is a question here. Let me take a question here. So from Rajiv, Rajiv Abraham is saying, does MLflow integrate into AWS SageMaker? So when the model is made by SageMaker, it shows up in the MLflow UI.
So between SageMaker and MLflow, it's really just code. So we just use the MLflow APIs. So for MLflow tracking, when running a job in SageMaker, it will hit the MLflow UI. And then same with the model registry. So we're not necessarily saving it in SageMaker and then MLflow picks that up. It's more like SageMaker has the line of code that says, okay, save this to MLflow.
Okay, got it. And then one more question also from Nasrun Chung. Is the DynamoDB online store a mirror of the offline store?
Somewhat. So what it does is it takes just the most recent features that are in the offline feature store. So it always updates them with just whatever's the latest.
Okay, awesome. I think let me just ask one final question. So is there a monitoring for the recommender systems? Just a general model monitoring pipeline that you guys already built?
Yes. So our company uses New Relic as its monitoring framework. So we've just kind of hooked into New Relic there. So on the service side, we just use the the default Python New Relic agents for things like response time and errors and everything like that. Okay. For actual model performance, it's obviously a bit more tricky. So we're doing a lot of jobs to run these evaluations, but then we just figured if we're monitoring things in New Relic already, let's just write those metrics to New Relic, and so in one place we can see, okay, here's how our API is doing, here's how our model's doing.
Oh, awesome. Well, this is cool. Thanks so much. I really appreciate you taking time out to come chat with us and to answer all our questions. I think that's all we have.
Yeah, thanks everyone. Those were great questions too.
Yeah, thank you.
Yeah. And folks still online, please go to the polls and give feedback. We definitely appreciate that. And then if you have time to, you can go to the, I think to the booth section and kind of check out the companies that are still around and just chat with people. Thank you so much. Appreciate it.
Thanks, everyone.
Thanks.
Yeah.